to focus on the third week. And for the slide, when you get the slide, all of these are actually clickable, and it can take you to the various sections where you want to, for each of the sections, to see what it is that you're looking for. So this week, our focus is going to be on data cleaning and exploratory data analysis. Some of the things we'll look at is data quality and cleaning decisions, because like I mentioned, when you get data is not automatically clean in all of the instances. Sometimes your data might come in a little messy, and then when you have messy data, you have to prepare the data. So when it comes to data preparation can be one of those things that take a lot of time when you are doing some data analysis work. Collecting and then cleaning up that data can be a hassle sometimes, or more importantly, it consumes most of the time. I'm thinking maybe anything between 50 to 70% of the time that you spend in a data science project might actually be spent in cleaning up the data and preparing it in a format that would make it ingestible for analysis and for the final work that you need to do on it to be able to extract meaningful information from it. So that's what tends to happen. So one of the things we'll look at is issues around data quality, and cleaning decisions. I did mention last week about exploratory data analysis, which is essentially what you do to understand your data. In other words, you are exploring the data, to understand what exactly is in the data set that you have. It's easy if you have just one sheet of Excel sheet, you can quickly eyeball it and tell what it is, right? But when you have a million lines of data, or data that is semi-structured or unstructured, it's very difficult for you to know what's contained in that massive data. So one way to easily figure out what's going on, just with maybe a line of code or two, is using exploratory data analysis. And this is a broad topic. I don't mean to make it that simplistic, but generally what you want to do is to figure out what's going on, explore that data to figure out what's going on with that data. So we're going to look a little bit at applied exploratory data analysis and memo writing, and then we're also going to go into some practice. And I haven't mentioned a lot about the capstone, but we're also going to do the mastery check. But most of what we are doing is eventually going to feed into the capstone that you're doing. So I would need to send out a separate memo so that you can begin to think about the capstone you're going to do, and go to each of the slides, week 1, 2, and 3, to see the progression, how you are supposed to advance with your capstone. And you're going to see it at the ending part of each of the slides. And we're going to do some deep dive later in the class. So let me start from the first part, data cleaning and exploratory analysis. This is more like a summary of the entire topic that we're going to cover today. We're going to learn to diagnose data quality problems before analysis. We would look at how to apply cleaning strategies to missing values. Sometimes you have duplicates in data. Sometimes there are issues with the type. So for example, maybe the way the intake application was set up, right? It did not try to exclude, for example, someone in a place where you have, for example, age. That field is supposed to, for example, only accept numericals, but somebody might set up that page in such a way that it can accept any number. So someone comes there, doesn't want to give their age, and instead of typing their age, which is maybe 63 years, they will just type um, a string. They will say something like no or yes, right? If you want to, for example, take an average of all of the years, that yes now will now throw off all the other data. So those are all the kind of things you want to check. And sometimes you have outliers, right? Let's say you're asking again about age. Typically you see most people would live between 100 and 120 years. All of a sudden someone there goes to enter that their age is the age of Methuselah, 1000. Yeah, you need to be able to go in there and see, oh my God, it's not possible for someone to be 1000 years. That's an outlier. And then you need to know what to do about that. Either take an average of all the other ages and put a number there, or just decide to remove that line of data. So those are some of the things that you do when you're doing your cleaning, data cleaning. We want to use exploratory data analysis to investigate distributions, relationships, and anomalies. So those are some of the things exploratory data analysis can help you do. So what's the mean of my data? What's the minimum? What's the maximum value? What are the different quantiles? Those are all the kind of things exploratory data analysis can help you do. And then eventually we would have to produce an exploratory data analysis memo that translates charts into evidence based claims. A lot of the things that you might end up with your exploratory data analysis is you end up with beautiful charts, bar charts, you end up with graphs and all of those things. But we want to be able to go beyond that to actually make evidence-based claim by the reading of that data, which is what we now here refer to as the EDA memo, some kind of memo that you can now hand off to stakeholders to immediately look at it and see exactly what it is that you're trying to say. So the outcomes for this topic is we want to summarize data quality issues. We'll talk about them. We want to choose appropriate missing data strategies, value strategies. So if you have missing values, what do you do? Different people do different things, right, when data is missing. So for this, what we want to do is to look at some appropriate ways of handling missing data. The third outcome is we need to eventually, at the end of this class, you should be able to detect and reason about outliers, understand outliers, their impacts, and what to do about them, hopefully. Then we want to conduct univariate, biovariate, and multivariate EDA. And this is when you have multi-variables, right? You have to deal with two, one particular variable that you want to pay attention to, or you want to pay attention to two variables, or you're looking at in some data science problems, you have hundreds of variables, right? So that is part of the focus today. And then we want to introduce visualization responsibly. And when I say responsibly, some people just, because they can create a chart, a bar chart and all of that, they just go all in and just create things. And sometimes the color themes are wrong, or you're using the wrong chart for whatever it is that you're doing. Part of this is to give us the skills to be able to interpret visualizations responsibly, so because visualizations can be made to say whatever a biased party has to say, but this will help us, interpret them responsibility. And then finally will be to create an EDA checkpoint. Again, EDA means exploratory data analysis checkpoint for the capstone. So data quality and cleaning decisions. So you see there are issues around missingness, in other words, missing data, outliers. Sometimes you have duplicates, and then what's the logic I can use for my cleaning? So dirty data creates false confidence. That's the thing. If you just get data and you just want to use it directly as is, you might get results that you celebrate, but actually those results, might be wrong. And I'll give you a typical example. Like I mentioned, somebody could potentially add their age as 1,000. So if I have 10 people giving me their ages, right? One person is probably 17, 25, 18, 20, 63, blah, blah, blah. And then I have 1,000. If I decide to take the average of their age, right, that outlier, the 1,000 is going to throw it off, right? And it wouldn't make sense anymore. So those kind of things, dirty data can create false confidence where all of a sudden you're like, oh, the average of their age is 150. Oh, that's a good thing. No, it's not, because what threw you off that data is the 1,000 there. It's an outlier. So dirty data can create false confidence. Clean decisions can change conclusions, which is a corollary of this, of if if you don't clean your data, you probably will get some results, and that those results will not necessarily be correct. If you decide to clean your data and you don't use responsible cleaning strategies to do it, you might also influence the outcome. So the goal here is to be able to make sure we are using responsible um, making responsible cleaning decisions. And an example of what I will mention is, let's say, same thing. You have those 10 ages, right? And you've listed them, and then you have this that's 1,000 years. And that 1,000 is clearly an outlier. So one person could decide, you know what, I'm going to remove the 1,000, and in place of the 1,000, put zero. If you put zero in place of the right 1,000, it could skew your results, right? So sometimes what people do is take an average of all the other ages, and that average would be the number that would replace that 1,000. But there are different strategies of doing this, which is the point. Cleaning decisions can change the conclusions. So you want to be able to make the right decisions so that your conclusions are not skewed, and especially skewed in the form that they make your conclusions meaningless. So the other thing to note is there is rarely one universal correct cleaning choice. So that's where experience comes in. You need to know of the various ways in which you can do your cleaning, and then use good judgment to decide how to handle the cleaning. Professional analysts document what they changed and why. That's one of the things about a good data science professional. Whenever you make any changes, you need to be able to document those changes, and explain why you made those changes for a lot of reasons. For yourself, if you come back in 1 year and you want to look at that data, you want to be able to remember precisely what changes were made and why it was made. Sometimes if it is discovered that your conclusions, the conclusions that were expected are not what was gotten, and it seems like, what you have done, maybe your choices in your bad data cleaning choices has skewed the results. Somebody might begin to think, oh, maybe this person was trying to manipulate the data. But if you have a note that you left early enough of what was changed and why it was changed, it will be easy to, for people to see that there was no ill intent in what you're doing. The third reason I would say is, when you do this and you're working in a team, other members of the team are apprised of what you're doing and why you are doing. So technically, data cleaning is actually risk management. So, for example, let's look at common data quality problems. One of them is you have missing values, right? For example, the age was not recorded. Like what I mentioned to you, let's say the person that entered 1,000 years didn't even enter any dates, right? If I take an average of all of the dates, then it's going to skew the results. So this could be a problem. The risk of that is that biased estimates, if missingness is systematic, right? There could be a bias, for if you start making some estimates, right? And let's say there are so many missing things, and then you begin to make all of those, it could literally create a systemic problem for the outcome of that data. So you could also have problems of duplicates. And what happens with duplicates, an example of it is where you enter a customer record more than once. That could be a problem, especially, for example, if you had something, it's financial data. Let's say a customer a customer has money left with your organization. Let's say you're owing a customer $1 million, and all of a sudden that entry was put in twice, and let's say your profits, for that quarter was supposed to be 2 million. Those that double entry would all of a sudden cut down on your profit, you know, and contrary-wise, it's going to inflate that count. In other words, it's going to, skew something in the result. So you want to make sure that whenever there are duplicates, that's correctly dealt with, because it introduces the inflated count risk. There's also the type error, the type of the data. So we have different data types. You have string, you have floats, you have all kinds of data types. And in a column, when you enter data, especially if it's structured data, you want to make sure that the data that is being included in that column is the specific type that is supposed to be in that column, you know. So the recommendation is that when you're creating applications that intake applications that help you collect that data, right? You want to hard code them in such a way that they only accept the type that is specific for the column that is it's supposed to. So definitely the type error is a major error. An example of it is date stored as text. If you're supposed to put in a date, which will be, for example, 06/27/2026, and in place of it, you go put a text, then it will create an invalid time analysis, because with that, you don't even know when that data was collected anymore. So it creates invalidity in the time analysis. Outliers, I did already mention outliers, like somebody entering their age to be 1,000 years. Or another example is somebody enters a negative age. It's not possible for someone to have a negative age. How old are you? I am minus 20 years old, or extreme fair, you know, putting in something that is really large. So what it does is that it distorts the means, which is, when we say means here, I'm talking about the average. It distorts the average or affects the model fit. So if you're trying to fit a model and you have so many outliers, all of a sudden, it's very difficult to accurately fit. And even when you fit, you notice that there will be a lot of errors in that model. And then there could be the problem of inconsistent categories. For example, male, M, are you using M? Are you using male as in capital M or small l? So if you don't hard code the inputs, say column, so that people enter a specific one, choose either one of these, right? When you begin to do the analysis, the system might actually see this as 3 different entries. So there has to be consistency in choosing what your categories are. And for example, if you have all of these coming with your data, you have to go in and change all of them either to M, to male with a capital letter, or to small male, or else you're going to end up getting fragmented groupings. So one of those things, as we just mentioned, is missingness. In other words, something is just missing. But it's not just one thing, right? There are different ways it can happen. So missing completely at random, something might be missing that is even unrelated to the data, missingness unrelated to the data, missing at random, you know, missing not at random. This is missingness related to unobserved or missing value itself, right? The type of missingness influences whether we are going to drop it, we are going to input it, we are going to flag it, or we are going to, or whether, sorry, dropping, imputing, or flagging it is appropriate. So when something that is all related gets put in there, then something like that probably needs to be flagged, right? Or we just have a situation where something is missing, then maybe we might just need to input something there. There are all kinds of situations, and some of this will best be served by looking at specific examples. So, so there are different ways you can, deal with cleaning. You know, for example, let's say you have few random missing values. If they are just few and I have 1,000 rows, right? And just there are a few missing values. So instead of going to mess around with those values because they might not be consequential enough to affect the outcome, I could just decide, what, let me just drop those or delete those rows. You know, when it's appropriate is when the loss or no bias concern, there are no loss, or no bias concerns. So if by removing this and taking the average, if it's not going to fundamentally change anything, I probably will just drop off those rows. Um, Another issue is important numeric field missing. You have a numeric field that is missing, right? So one of the things, like I mentioned, is you could take a median of all of the other values and just use the median. In some cases, you might want to use the mean. So if I have some outliers, right? But you looked at those outliers and those outliers are actually correct, I probably will use a median. But if I have these outliers there, that when I take the mean, I take the mean, all of a sudden it's going to alter the mean. I'll probably go for median. But if I don't have outliers and I can easily take an average, I probably would choose mean. So missingness is manageable and documented. So for something like this, you can just impute some of this and then document what you have done. Or we can just develop a model, of how we, maybe have beside mean, median, we can just come up with a way to just come up with a number to fill that gap. So missingness itself, informative. So we create missing flag. Absence may signal behavior. So that's one of the things we could do for a particular case like this. And we have a particular case where something is missing or it's informative, and so for example, I'm looking for an example that will fit. Someone enters something they are not supposed to enter there, or I keep seeing so many people enter the same thing, but it's wrong, then I could essentially flag that situation, which can help in the next data collection, uh, or probably it was completely omitted. And it's not just one person omitting, it's so many people omitting that stuff, right? And I want to flag that because the absence of data or missingness, as it were, might signal a behavior or it might signal a lapse in your design or something. So in some cases, like I talked about the person entering their age, uh, entering their age to be 1,000, or let's say you did a measurement, and the measurement the results that you see there are practically just not possible, right? They're practically, maybe it's something about the weight of a car. And then when you look at the weight of the weight of the car is so small that even the tire, the weight that was given there is even less than the weight of the tire. Then there could be problems. So it's an invalid and impossible value that was entered. In that case, you want to correct or remove that entry. When is that appropriate? When entry or measurement, when there is entry error or measurement error. Sometimes you might have an extreme but plausible value. Now, this value is, oh my God. So we are looking at people's net worth, and someone's uh, net worth is reported as 1 trillion. That is extreme. But again, Elon Musk just became a trillionaire. That means it's plausible. It's extreme, but it's plausible. Possible action, you probably could keep and analyze that separately, and when it is appropriate, it could be an important signal of something. So when I see 1 trillion net worth right now, it's a signal that something has changed in the quality financially. So this is for missing values. So, we are going to go, make sure you look at our Jupyter notebook, because that's where we're going to, or you could use this, to help figure out missing values, right? This is a potential code. This right here is Titanic data. So you can actually copy this eventually and put it in your Jupyter notebook and try to run it. So here essentially we are importing pandas, and then we are using this as the shorthand for pandas. We import Seaborn and use this as the shortcut for it. And this is your URL. And now I'm reading that data, because this is our data. Our data is actually URL. So I'm using this to read this. So once you do this, it's going to read it and then read it in for you. And then the next thing is we want to find out missing data, right? So we are saying our data frame, which we already have, and then we have this. We're trying to find anywhere where you have not available. In other words, that's some kind of missing data. Got some, want to sort the values, and then in descending order, right? And then you get missing. And then once you get that particular column of where everything is missing, then you want to look for those that are greater than or equals to 0. Right? Greater than or equals to 0. Anything greater than or equals to 0, that's how you find out all of those missing values. So how do you handle missing values? An example strategy: impute age with median and embark with mode. So just 1 minute. So to continue, you're looking at age imputed will be equals to a data frame age dot. You want to fill this with the median. So this is me, where there are gaps, I want to fill it up with the median, or I want to fill it up with mode, right? So this is you documenting it, right? This preserves rules, but may reduce natural variability, right? Because in some cases I'm using median. And what do I mean by using median? What this code is essentially doing is just getting all of those values and then taking their median and filling it. Well, we're going to see that more clearly in the Jupyter notebook. So for outliers may be data errors. rare but valid cases or strategically important signals. So sometimes you just see an outlier there, right? Something that you do not expect, a value that you do not expect. Now, just seeing a value that you do not expect does not automatically mean that that data is an error. So that's why you need to tread cautiously, you need to investigate. Because in some cases, there are rare but valid cases, or they could be strategically important signals to something, that something is going on with that data. So, which is why you do not remove outliers automatically. One of the things you want to do is to ask whether the value is physically possible, whether it's contextual in this particular context, is it even plausible? And then the third thing is it going to skew my data, right? Is it influential? And then you can use box plots, IQR, Z-scores, and domain knowledge to handle data. Because with some of these, it can actually show you how severe that error or signal is. So exploratory data analysis is actually a very disciplined investigation of data. So it's not just random plotting, create charts, blah, blah, blah. No, it is not random plotting. Each chart should help answer a question. So when you are plotting these charts from your exploratory data analytics, you want to make sure each chart that you are creating is meaningful. It needs to be able to refine your hypothesis or reveal a risk, because the goal of the EDA is to be able to make you understand what's going on with that data. And if you're trying to come up with a hypothesis for a problem that you need to solve in the future, all of that data is supposed to help you really do that. So EDA, right, should move from broad structure to specific relationships, right? Every chart should be followed by interpretation. What is it saying, and why is it exactly saying it? That's what the EDA should be focusing on. So look at some EDA level questions, right? Some of the EDA level questions would be, just 1 minute, we're talking about univariate analysis. We talked about that, multivariate analysis, blah, 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 all of that. So often, I was mentioning something that, a univariate analysis, what it actually does, it examines a single variable at a time to investigate the distribution and patterns of that data. So you could have 10 different variables, but when you're doing univariate analysis, you're focusing on one particular variable and you're trying to figure out how that variable affects every other thing. Or in bivariate um, analysis, what you're doing is you're using two variables, to check against every other thing, right? And in multivariate analysis, you're examining three or more, variables simultaneously to understand the complex relationships, right? Correlations, and how, those three or more variables jointly affect the outcome. That's what you're doing there. So in this particular case, right, we're looking at the different levels of EDA analysis. So univariate, at the univariate level, one of the things the question we want to ask, what does one variable, that particular variable, let's say you're talking about temperature, how does it look like and how does it affect every other thing? So examples will be, you use something like histogram or count box or box plots, often, you're checking that one thing against time or something, right? So, or and that's for univariate analysis. But if I'm doing a bivariate analysis, I'm looking at these two variables. How do they relate to each other, right? So, for example, I'm doing something between my X and Y axis, trying to figure out something. So a scatter plot can be an example of you doing a univariate analysis, your grouped bars, box plots, and as you do those box plots by different groups, that could be it. And then when it comes to multivariate analysis, how do several variables interact, right? Like I mentioned, we're looking at two or more variables, how they interact and affect the outcomes. That's where you use things like pair plots, heat maps, facets. And then you also have your grouped analysis. And the question is, how do patterns differ by segments? I'm trying to look at what's happening in different geographical area, for example, in terms of sales, right? Or some other things. These are some tools you use, like your pivot tables, group by summaries, and all of that to do those analysis. But then when you're doing it, you need to know exactly what variables you're working with, why you're working with those variables, and what specific outcomes you want to, because eventually it's going to be very helpful for stakeholders to be able to now use that data to make the next level of decisions that need to be made. So this, for example, is a case of univariate distribution. Matplotlib, which is the plotting tool that you have, that you can use, for your Python. We're trying to, and this is coming from the data we already had, right? Age imputed, and then you want to create a histogram with 20 bins. And then this is the title. This will help create the title, the X label, the Y label, and then this will help display it. So again, all you need to do with this is go copy each of the codes, line it up on your Jupyter notebook, and then run it, and you will see exactly what's going on here. So this is where I want to do bivariate analysis. I want to plot two things, so survival by class. We're looking at the survival by class. It's still that Titanic data that we had, right? And you can copy all of this and try to run them. Eventually, you get your plot title, and then you get your Y label, the survival rate. And here you're essentially looking at the survival rate by the various classes, right? So eventually you're going to look at the survival over time. So correlation map, you can create a correlation map, and you essentially can use this tool, to show the correlation, and then you see changes in the color of the map, and that can actually give you more information about what's happening with this data too. So for correlation warning, correlation actually measures association, not causation. So that's one way that you've seen an outcome doesn't mean, it just shows that two things are associated. It's not saying that one thing is caused by the other. So confounding variables can create misleading relationships, right? Non-linear relationships may not be captured well by simple correlation. If relationships are not linear, then a simple correlation might not just capture, the relationship between them well. And then if you have just small data, it's not something that works well with correlation when you're creating those maps. So small samples can create unstable correlation estimates. So we are going into still based on the Titanic data that we shared before. One of the things we come here, we want to turn that exploratory output into defensible findings. After you've gotten all of that, some of the questions you might ask is, which passenger characteristics appear associated with survival? These are questions you could be asking, that can inform your data analysis. How does survival vary by passenger class? How do sex and age relate to survival? What role might fare and family size play? And what limitations prevents causal claims? So, and again, I want to make sure we are all familiar with the Titanic data, because if you're not familiar with the Titanic data, that would be something that would really be good that you study before. It helps you understand this. So while you're studying this, just go and do a search, an internet search for Titanic data, and you would see a lot. There's a lot of information about Titanic data, and it was based on the accident, shipping accident that happened in April 15th of 1912. You know, during the maiden voyage of that fantastic uh, ship, right? They had the infamous wreck that happened. There was an accident, and a lot of people died. Um, and the ship was the RMS Titanic. They had initially said that this ship was unsinkable, but unfortunately, it's collided with an iceberg. Um, and then, of course, there were different classes of people, poor, rich, and all of that. And there weren't enough lifeboats for everyone on board, to escape. Well, it turned out that because of that, 150, I think 1,502 of the passengers on that ship died out of a total of, 2,224 passengers and crew. So, and since that happened, the data for all of that was collected, and then that has been a basis of a lot of data analysis. That data set has been used to teach maybe millions of data scientists, and other data professionals analysis of data. So based on that data for the EDA, one of the things is which passenger characteristics appeared associated with survivor. Is it their age? Is it their economic status? Is it their sex? Those are some of the questions that you can answer using that data. How does survivor vary by passenger class? Of course, there were people in different passenger classes. They had first class, they had second class, and they had third class. So the question is, were some people in were there more survivors from people in first class than people in second class? How were people in the third class affected? So if you have all of this data, you should be able to query all of this and get all of that information using exploratory data analytics. So the other thing is, how do sex and age relate to survival? You know, did more females survive? Did older people survive at a greater rate than younger people? Those are all the things you can find out. What role might fair and family size play? You know, what implications prevent causal claims? What limitations prevent causal claims? So those are all the kind of questions your exploratory data analysis can answer. So if you want to do a memo, this will be a structure of that memo, right? These are some of the sections that would be recommended for a memo for your exploratory data analytics. You want to talk about the data quality, what cleaning decisions you made, your key findings, your visual evidence. This is where you put your graphs, your pictures, slides, and then you want to talk about the limitations of your EDA and then what your next steps are. So for data quality, what would you include? All of the missing values, the duplicates that you found, type issues, and then the outliers. For the cleaning decisions, you want to say what changed and why it changed. Your key findings, you want to talk about 3 to 5 evidence backed patterns. Your visual evidence, of course, your graphs, charts, and all of that, you want to put them. And then you want to speak to your limitations. If there were any limitations or any bias you saw with the data, you want to report that. And then you want to say, okay, it's okay, go ahead and start modeling, or you will be like, we need additional data, or the data we have is insufficient, it's or is biased and all of that. So that's where you include that in this section. But eventually that's how you create your EDA memo. This is a recommended structure. So Now, we're going to go do some of the lab, and I would also um, come to this place. Uh, yeah, so for the rest of this, I would want you as the class, to take where this will be where you spend your time and to do your own recaps, you know. So as a final takeaway, EDA is a disciplined investigation. It is not decoration. Cleaning choices affect your conclusions, and visualizations require interpretations. A strong EDA memo prepares the ground for modeling. So EDA, very, very important. That's where you do all of your cleaning, strengthen your hypotheses